Now in this lecture I'll answer on two questions. In the first question we find out the area of this pentagon ABCDE, and in the second question we find out the area of this grid shape. So we start with the first question. In the drawing we have pentagon ABCDE. So what is a pentagon? A pentagon is a flat closed shape with 5 straight lines and 5 interangles. This is pentagon ABCDE. It has 5 sides, 1, 2, 3, 4, 5, and 5 interangles. Okay, so our task is to find out the area of this pentagon ABCDE. So first of all, we join points E and C together by a straight line. And we join points E and B together by a straight line. And we'll also extend side BA of this pentagon ABCD by a straight line in such a way that the extended part will be equal to x units in its length. We define this point as point M. When you extend a straight line by a straight line, the result must be a straight line. We extended the straight line BA by a straight line, and therefore the result BM must be also a straight line. So if we focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So each angle we have at the upper side of the straight line BM at point A, we have this angle is equal to 90 degrees in size, plus this missing angle in total must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. Again, according to our construction, the extended part AM is equal to x units in its length. In the next step, we join points E and M together by a straight line. Joining points E and M, we created this right triangle EMA. So in the next step, we prove that those two right triangles are similar to each other according to side angle side rule. So while those two right triangles are similar, we prove that those two triangles can go into each other according to side angle side rule. So while those two triangles can go into each other. So we have to prove that the right triangle EMA can go into this right triangle EDC according to side angle side rule. So we have the right triangle MEA and the right triangle EDC. So what those two right triangles can point to each other? First of all, side MA of this triangle EMA is equal to side ED of this triangle EDC. They are both equal to 1 and therefore they are equal to each other. So if you know, again, side MA of the right triangle EMA is equal to side DC of this triangle EDC. They are both equal to X and therefore they are equal to each other. So MA equals to DC, and again side MA of the right triangle MEA is equal to side DC of the right triangle EDC. They are both equal to X and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So this is angle EAM, in the right triangle EAM, and it is equal to this angle, the actual angle EDC, in the right triangle EDC. And again, I have to solve that angle EAM in the right triangle MEE is equal to angle EDC in the right triangle EDC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, side EA of the right triangle MEA is equal to side DC of the right triangle EDC. They are both equal to 1 and therefore they are equal to each other. So if you know, ME equals to ED equals to 1. Again, side ME of the right triangle MEE is equal to side ED in the right triangle EDC. They are both equal to 1 and therefore they are equal to each other. So if you prove that those two right triangles can go into each other according to side angle side rule. So I write it down. So if you prove that the right triangle MEA can weld, this is the side of can weld to the right triangle EDC. According to side angle side rule. That is to say, if we prove that those two sides and the angle that is included between those two sides, that is the right angle, in the right triangle EMA are correspondingly equal to those two sides and the angle that is included between those two sides, that is also 90 degrees, in this right triangle EDC. And therefore, those two right triangles can go into each other according to side angle side rule. We have two sides and the angle between them, in triangle EAM, that are correspondingly equal to those two sides and the angle between them, this right triangle EDC. And therefore, those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we derive two things. The first thing is that the areas of those two right triangles are equal to each other in their areas, because any two triangles that can go into each other, they must have also the same areas. So there are this green right triangle EDC. Must be equal to there of this green right triangle EAM. So if we define the area of this right triangle EAM as Z, that is to say it is equal to Z coordinates in its size, then the area of this right triangle EDC must be also equal to Z coordinates in its size because they have the same areas. They have the same areas because they can go into each other. The second thing that we will derive that from the fact that those two right green triangles can go into each other, that side EC of this right triangle EDC is equal to side EM of this right triangle EMA. And side EM equals to side EC. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore those two corresponding sides must be also equal to each other and their lengths. E equals to EC. So, in the next step, we will prove that the big triangle MEB can go to the big triangle BEC. We prove that those two triangles can go into each other. So, as we know, we have to prove that triangle MEB can go into this triangle EBC. We will prove that they can go into each other according to side rule. So, why those two triangles can go into each other? But before that, we find out the length of side MB of triangle MEB. What is the length of MB? MB equals to MA plus AB. MB side MB of triangle EMB is equal to MA plus AB. So MB in total equals to MA is X, plus AB is 1 minus X. So in total MB equals to X minus X is 0. We have to only with 1. MB equals to 1 unit in its length. So she found out that side MB or triangle MEB is equal to 1 unit in its length. We continue with the proof that triangle MEB can go to this triangle EBC according to side also. Why those two triangles can go into each other? First of all, side MB or triangle MEB is equal to side CB of this triangle EBC. They are both equal to 1 and therefore they are equal to each other. Repeat again. Side MB of triangle MEB is equal to side CD of triangle EBC. They are both equal to 1 and therefore they are equal to each other. In addition, we have here, we only found out that because of the fact that those two triangles can go into each other, side ME is equal to side EC. So side ME or triangle MEB is equal to side EC, this triangle EBC. And again, So what we already found out, side ME or triangle MEB is equal to side DC or triangle EBC. And finally, EB is the common side. You can see that EB belongs to triangle EMB. It is also belongs to triangle EBC. So EB is the common side that belongs to both triangles. So you can write down that EB equals to itself. It's the common side that belongs to both triangles. Again, EB equals to itself as a common side that belongs to both triangles. So if we prove that all the three sides of this triangle MEB are correspondingly equal to all the three sides of this triangle MEC. And therefore those two triangles can go into each other according to side rule. So I'll write it down. If you don't know that triangle MEB congruent, this is the side congruent to triangle EBC according to side rule. And from the fact that those two triangles can go into each other, we derive that they have also the same areas. That is to say, the area of triangle MEB is equal to the area of triangle EBC. Again, the area of triangle MEB is equal to the area of triangle EBC because they can go into each other. In the next step, we will find out the area of this triangle MEB. What is the area of triangle MEB? The area of any triangle equals to the base of the triangle times the height over 2. So the area of this triangle MEB will be equal to the base MB times the height AE over 2. And again, the area of this triangle MEB is equal to the base MB times the height AE over 2. We already found out that MB equals to 1 times AE also equals to 1 divided by 2. So in total, the area of this triangle MEB is equal to 1 times 1 over 2. 1 times 1 is 1 divided by 2. So in total, we found out that the area of triangle MEB is equal to 1/2 square units in its size. You can see, I down here that the area of the MEB is equal to 1/2 square units in its size. And from this equation, 1/2 equals to the area of the MEB equals to the area of the EBC. We derive that the area of triangle EBC also equals to 1/2 square units in its size. The area of triangle EBC also equal to 1/2 square units in its size. So the area of triangle MEB plus the area of triangle EBC in total the area of triangle MEB plus the area of triangle EBC equals to the area of triangle MEB is 1/2 plus the area of triangle EBC is also 1/2. 1/2 plus 1/2 is 1. So in total, we found out that the area of triangle MEB plus the area of triangle EBC equals to 1 square in its size. This is the big quadrilateral EMBC. The big quadrilateral EMBC consists of those two triangles, triangle EMB and triangle EBC. And therefore, the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of the big quadrilateral EMBC will be equal to the area of this triangle MEB plus the area of triangle BEC. Consists of those two shapes. And we already found out that the area of triangle EBC equals to 1/2 square units in its size, plus the area of triangle EBC is also equals to 1/2 square units in its size. 1/2 plus 1/2 is 1. So in total, we found out that the area of the big quadrilateral EMBC is equal to 1 square units in its size. But quadrilateral EMBC consists of two other shapes. It consists of this quadrilateral EMA and this quadrilateral ABCE. So the area of quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of this green quadrilateral EMA plus the area of this quadrilateral ABCE. So write it down. We found out that the area of the big quadrilateral EMBC will be equal to the area of this green quadrilateral EAM plus the area of this quadrilateral ABCE. And from this equation, the area of triangle EMBC equals to 1 equals to the area of triangle EAM plus the area of quadrilateral ABCE. We derive that the area of triangle EAM plus the area of triangle ABC, the area of triangle EAM plus the area of quadrilateral ABCE equals to 1. And those two sides are equal to each other. Okay. So the area of triangle EAM plus the area of quadrilateral ABCE is equal to 1. Those two sides are equal to each other. But according to our definition, the area of this triangle EMA equals to Z. So you can substitute the area of triangle EAM by Z. And we get that Z plus the area of quadrilateral ABCE is equal to 1. Our task is to find out the area of this big pentagon ABCDE. So what is the area of the big pentagon ABCDE? The area of pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of the big pentagon ABCDE must be equal to the area of this green triangle ADE plus the area of quadrilateral ABCE, because it consists of those two shapes and not anything else. So the big pentagon ABCDE must be equal to the area of this green triangle EDC plus the area of this quadrilateral ABCDE. ABCE. Quadrilateral ABCE. Repeat again. The area of the big pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the green triangle EDC plus the area of quadrilateral ABCE. We already found out that the area of this quadrilateral EDC equals to Z, correct, inside. So we can substitute the area of this green triangle EDC by Z. Plus the area of quadrilateral ABCE. So if you found out that the area of pentagon ABCE equals to Z plus the area of quadrilateral ABCE. But we already found out that Z plus the area of quadrilateral ABCE equals to 1. So if you like it, that Z plus the area of quadrilateral ABCE equals to 1, according to what we already found out. And from this long equation, we derive that the area that we are looking for in this question, that is the area of pentagon ABCDE equals to 1 square units in its size. So written down, once we found out that the area of the big pentagon ABCDE is equal to 1 square units in its size. So we finished with the first question. Repeat again. The area of this big pentagon ABCDE is equal to 1 square units in its size. We finished with the first question. In the next step, I present to you the second question and also the second question of this lecture. Our task in the second question is to find out the area of this ring shape. The green shape is actually triangle AMB, so we have to find out the area of triangle AMB. It's given us the question that AB, chord AB is the diameter of the circle. AB is the diameter of the circle according to what is given to us. In addition, we know that AP equals to 9, BQ equals to 4, PQ is a tangent to this circle at point M. In addition, we know that those two angles are both right angles. Again, our task is to find out the area of the green shape that is actually the green right point A and B. So first of all, we can implement rule 7 in our drawing. Okay, quickly rule 7. According to rule 7, if you verify an angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. Chord AB is the diameter of the circle. This is peripheral angle ACB that subtend on chord AB, that is the diameter of the circle, and therefore according to this rule 7, peripheral angle ACB is equal to 90 degrees in its size. So any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, peripheral angle A and B subtend on the diameter of the circle. And chord AB, that is the diameter of the circle, and therefore according to rule 7, is equal to 90 degrees in its size. In the next step, we will define angle PAM. This angle is alpha. So in the right triangle APM, this angle equals to alpha, this angle equals to 90 degrees, this angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in an triangle. PQ is a tangent to the circle at point M. Therefore, PQ is absolutely a straight line. PQ is a tangent, it is absolutely a straight line. So, if we focus on the upper side of the straight line PQ at point N, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. For which angles we have at the upper side of the straight line PQ at point M, we have this angle that is 90 degrees minus alpha, plus this angle that is 90 degrees, plus this missing angle that is angle BMQ. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. So, I'll write it down. 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ. Total, the sum of those three angles must be equal to 180 degrees according to rule 3. Ninety degrees plus 90 degrees is 180 degrees, plus the missing angle BMQ minus alpha is equal to 180 degrees. Here we have 180 degrees on both sides of the equation, so 180 degrees will get cancelled, and we're left only with the missing angle BMQ minus alpha equals to 0. Here we will add alpha to this equation, and we get that the missing angle BMQ is equal to alpha degrees in its size. This is the missing angle BMQ, is equal to alpha degrees in its size. So in the right small triangle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. It's very easy to see from the drawing that those two triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. Those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So we should find out that all the figures of this big right triangle APM are correspondingly equal to all the angles of this right small triangle BMQ. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. I should find out that the big right triangle APM is similar. This is the sign of similar of the right small triangle BMQ according to angle similarity rule. From the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM over side BQ of the small right triangle BMQ. Repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM over side BQ of the small right triangle BMQ. AP is 9. Over MQ. MQ is the missing side. MQ is the missing side, so left as it is. And it is equal to side PM. PM is the missing side, so we leave it as it is. Over BQ. BQ is 4 according to what is given as the question. So in total we found out that 9 over MQ equals 2 PM over 4. Here we will cross multiply this equation. And finally we get that 9 times 4, that is 36, is equal to MQ times PM. And again we found out that MQ times PM equals to 36. In the next step, we will define the center of this circle. This point is point O. So OA is the radius of the circle. That we will define the radius of the circle as R. So OA equals to R. OB is also the radius of the circle. Is equals to R according to our definition. In the next step, we will join points O and M together by a straight line. Point O is the center of the circle. Point M is the point of the circle itself. Therefore, OM is the radius of the circle is equal to R. Here we can implement rule 1. Why? Because we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency or tangent PQ with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO according to rule 1. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction. That is to say, from this point O, that is the center of the circle, we will draw perpendicular on AP. Again, from point O, we will draw perpendicular on AP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching points of the perpendicular from point O and AP. This point is point L. By doing this construction, we can deduce the big quadrilateral LOMP. Inside the big quadrilateral LOMP, we have 1, 2, 3 right angles. The sum of 3 right angles is equal to 270 degrees, so 270 degrees plus the side of this fourth missing angle. In total, it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OL, the big quadrilateral OLPM, we have 4 right angles. According to rule 5, any quadrilateral that has 4 right angles must be this rectangle in front of square. So we write quadrilateral LOMP is a rectangle because it has 4 right angles. In the next step, we will do another construction. That is to say, from this point B, we will do perpendicular on the radius OM. Again, from point B, we will do perpendicular on the radius OM. So actually, this angle cos 90 degrees and this angle also cos 90 degrees according to our construction. By doing this construction, we define the touching point of the perpendicular from point B and the radius OM. This point is point S. By doing this construction, we can do quadrilateral BSMQ. Inside this small quadrilateral BSMQ, we have 1, 2, 3 rectangles. And therefore, this fourth angle must be equal to 90 degrees in its size. And therefore, the small quadrilateral SPMQ is a rectangle because it has 4 rectangles. We know that the opposite sides of a rectangle are parallel to each other. Okay, again, the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP is parallel to the opposite side OM. Again, in rectangle LOMP, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. So if part of the straight line is parallel to another straight line, then the straight line AP itself must be also parallel to the other straight line OM. Therefore, AP is parallel to OM. So write it down. AP is parallel to OM. In the next step, I'll copy the parallel lines AP and OM and also the others AOB in the new page, and we implement on the new drawing Rule 50. So actually, this is line segment AP, this is parallel to line segment OM, and this is the radius AOB, that is copied from the original drawing. Again, AP is parallel to OM. Those two angles are defined as corresponding angles, and they are located between the parallel lines AP and OM, and therefore they are equal to each other in their sizes, according to Rule 50. So, okay, click on Rule 50. According to Rule 50, corresponding angles between parallel lines are equal to each other. In the drawing, we have line A that is parallel to line B. Line C cuts the two parallel lines A and B, those 2 points. Those two angles alpha and beta are defined as corresponding angles, and they are located between the parallel lines A and B. And therefore they are equal to each other in their sizes. That is to say, alpha equals to beta. So those two corresponding angles are located between the parallel lines AP and OM, and therefore they must be equal to each other in their sizes. So if you found out that angle APO is equal to angle MOB. According to Rule 50. is a triangle PAO. This angle is angle PAO. And it's equal to this angle, this is angle MOB. According to rule 50. So if we define the size of this angle as beta, then the size of this angle is also equal to beta because they are equal to each other. So if we found out that angle PAO equals to beta, this is the big angle PAO that equals to beta degrees in its size. And we also found out actually that the angle MOB also equals to beta degrees in its size. This is angle MOB is equals to beta degrees in its size. So in this right triangle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this first angle is equal to 90 degrees minus beta, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, this right triangle ALO, this angle equals to beta, this angle equals to 90 degrees, and therefore this first angle is equal to 90 degrees minus beta, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we will prove that this right triangle AO can go into this right triangle OSB according to angle side angle rule. So, why those two right triangles can go into each other? First of all, those two angles, they are both equal to beta and therefore they are equal to each other. So here angle LAO angle LAO in the right triangle ALO is equal to this angle SOB in the right triangle OSB. And again, if we found out that angle LAO in the right triangle ALO is equal to angle SOB in the right triangle OSB. They are both equal to beta and therefore they are equal to each other. Side AO in the right triangle LAO is equal to side OB in the right triangle OSB. They are both the other of the second is equal to R and therefore they are equal to each other. And again, if you follow the side AO in the right triangle ALO is equal to side OB in the right triangle OSB. They are both the other of the second is equal to R and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta and therefore they are equal to each other. So here this is again AOL. In the right triangle ALO, and it is equal to this angle, this is the angle OBS. In the right triangle OSB. And again, angle AOL in the right triangle ALO is equal to angle OBS in the right triangle SOB, they are both equal to 90 degrees minus beta, and therefore they are equal to each other. And therefore, those two right triangles can go into each other according to angle side angle rule. So, write it down. If we found out that the right triangle A and O congruent, this is the same congruent to the right triangle OSB according to angle side angle rule. That is to say, we found out that those two angles and the side that is included between those two angles, that is R, are correspondingly equal to those two angles and the side that is included between those two angles, that is also R, in the right triangle OSB. And therefore, those two right triangles can go into each other according to angle side angle rule. We have those two angles and the side that is included between those two angles in the right triangle A and O are correspondingly equal to those two angles and the side that is included between those two angles, that is R, in the right triangle OSB. Therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that NO equals to SB. NO equals to SB. Or side NO of the right triangle A and O is equal to side SB of the right triangle OSB. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides NO and SB must be also equal to each other in their lengths. So, if we define the length of side NO as x, then the length of side SB must be also equal to x because they are equal to each other. Note that the opposite sides of a rectangle are equal to each other. So in the big rectangle LOMP, side LO is equal to the opposite side PM. But LO equals to x, therefore PM must be also equal to x units in its length. Likewise, in the small rectangle SBQM, side SB is equal to the opposite side MQ. But SO is B, SO equals to x, and therefore MQ must be also equal to x units in its length. We already found out that MQ times PM equals to 36. Again, MQ times PM equals to 36 according to what we already found out. MQ equals to x and PM also equals to x. And again, MQ equals to x and PM also equals to x, so in total x times x equals to 36. X times x is x squared. This is equal to 36. Here we take a root out of this equation, and when we get that x equals to the square root of 36, that is 6. X equals to 6 units in its length. So x equals to 6. Here I know that x equals to 6. In the next step, we will implement the Pythagoras theorem on this small right triangle MBQ. Then again, we will implement the Pythagoras theorem on this small right triangle MBQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the derivation from Pythagoras theorem. So according to the Pythagoras theorem, in the right small triangle BMQ, BM squared, that is the square of the hypotenuse, equals to BQ squared plus QM squared. Then again, in the small right triangle BMQ, according to the Pythagoras theorem, BM squared, that is the square of the hypotenuse, equals to BQ squared plus MQ squared. BM is the missing side, so here it is. It is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16. Plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So in total, we should find out that BM squared equals to 16 plus 36. 16 plus 36 is 52. So BM squared equals to 52. Here we'll take a root out of this equation and finally get that the missing hypotenuse BM is equal to the square root of 52 units in its length. This is the hypotenuse BM is equal to the square root of 52 units in its length. In the next step, we will implement the Pythagoras theorem on this big right triangle APM. According to the Pythagoras theorem, the big right triangle APM, AM squared, that is the square of the hypotenuse, is equal to AP squared plus PM squared. And again, according to the Pythagoras theorem, the right triangle APM AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. AM is the missing side, so leave it as it is. So it is AM squared equals to AP squared. AP is 9, therefore AP squared is 9 squared, that is 81. Plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, we actually found out that AM squared equals to 81 plus 36. 81 plus 36 is 117. So AM squared equals to 117. Here we will take a root out of this equation and finally get that the missing side AM is equal to the square root of 117 units in its length. This is the missing side AM, is equal to the square root of 117 units in its length. Our task is to find out the area of this green shape. The green shape is actually the right triangle A and B, so we have to find out the area of the green right triangle A and B. We know that the area of any triangle equals to the base of the triangle times the height over 2. So the area of this green right triangle A and B will be equal to the base MB times the height AM over 2. And again, the area of the green right triangle A and B equals to the base MB times the height AM over 2. We already found out that MB equals to the square root of 52 units in its length times AM. AM equals to the square root of 117 units in its length divided by 2. So in total, we actually found out that the area of the green shape, that is actually the area of the right green triangle A and B, is equal to the square root of 52 times the square root of 117 over 2. We have the algebraic identity that states that the square root of A times the square root of B is equal to the square root of A times B. According to this algebraic identity, we get that the square root of 52 times the square root of 117 will be equal to the square root of 52 times 117, and you have to divide it by 2. $52 times 117 is equal to 6,084. So the area of the green shape, is the area of the right triangle A and B, is equals to the square root of 84 over 2. The square root of 84 is 78 over 2. 78 over 2 is 39. In total, we found out that the area of this green shape, that is the area that we are looking for this question. Is equal to 39 square units in size. And again, if you found out that the area of this green shape is equal to 39 square units in size. So we finish with the second question. In the next step, I will summarize the lecture. We start with the first question, of course. Our task in the first question was to find out the area of this pentagon ABCDE. So first of all, what is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interrogants. This pentagon ABCD, we have 1, 2, 3, 4, 5 sides and also 1, 2, 3, 4 interrogants. 3, 4, 5 interrogants. So in the drawing, we have pentagon ABCDE. Those two angles are both right angles. Side ED equals to 1, side DC equals to x, side CB equals to 1, side AB equals to 1 minus x, and side EA also equals to 1. Again, our test is to find out of this big pentagon ABCDE. So first of all, we join points A and B, E and B together by straight line, and join points A and C together by straight line. In the next step, we extended side BA of this pentagon ABCDE by a straight line in such a way that the extended part AM will be equal to x units in its length. So AM equals to x according to our construction. When you extend a straight line by straight line, the result AM is also a straight line. So if we focus on the upper side of the straight line BM at point A, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the areas on one side of the straight line is equal to 180 degrees. So which areas we have at the upper side of BM at point A? We have this area that is the right angle, plus this missing angle. In total, the sum of those areas must be equal to 180 degrees according to rule 3. Therefore, this third missing angle must be equal to 90 degrees in its size. In the next step, we joined points E and M together by a straight line. By joining points E and M, we created the right triangle EMA. In the next step, we proved that those two right green triangles can go into each other according to side against side rule. So why those two green triangles can go into each other? First of all, those two sides, they're both equal to x and therefore they're equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they're equal to each other. And finally, those two sides, they're both equal to 1 and therefore they're equal to each other. So if we found out that those two right green triangles can go into each other according to side against side rule. That is to say, if we found out that those two sides and the angle that is included between those two sides, that is a right angle, in this right angle EMA are correspondingly equal to those two sides and the angle that is included between those two sides, that is also a right angle, in this right green triangle EDC. And therefore, those two right triangles can go into each other according to side against side rule. We have those two sides and the angle between them in right triangle EM are correspondingly equal to those two sides and the angle that is included between those two sides in this right triangle EDC. And therefore, those two right green triangles can go into each other according to side against side rule. So repeat again, we should found out that the green right triangle MEA can go into the green right triangle EDC according to side against side rule. From the fact that those two right green triangles can go into each other, we derive two things. First of all, we derive that they have also the same areas. Any two triangles that can go into each other must have also the same areas. So the area of the green triangle EAM is equal to the area of this green right triangle EDC. So if we define the area of this green triangle EMB as Z, that is to say it is equal to Z square units in its size, then the area of this green triangle EDC must be also equal to Z square units in its size because they have the same areas. And the second thing that we derived is that those two sides are equal to each other. Why those two sides are equal to each other? according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say EM and EC, must be also equal to each other in their lengths. EM equals to EC. EM equals to EC according to the rules I mentioned. In the next step, we proved that triangle MEB can go into this triangle EBC. We proved that those two triangles can go into each other according to side rule. So why those two triangles can go into each other? But before that, we should prove that found out the length of side AB of triangle MEB. What is the length of side MB? MB equals to MA plus AB. MB equals to AM plus AB. So MB equals to AM, that is X, plus AB, that is 1 minus X. X plus 1 minus X, MB equals to X plus 1 minus X. X minus X is 0, so we're left only with 1. So in total, we found out that MB is equal to 1 unit in its length. So in the next step, we prove that those two triangles can go into each other according to side rule. So why those two triangles can go into each other? First of all, those two sides are both equal to 1 and therefore they are equal to each other. This is to say side MB in the right triangle MEB is equal to side BC in the right triangle EBC. In addition, we have found out that those two sides are also equal to each other. So side ME, triangle MEB is equal to side EC in triangle EBC. Okay, and finally, side EB is a common side that belongs to both triangles, so we can write down that EB equals to itself is a common side that belongs to both triangles. So we should prove that all the three sides of this triangle MEB are correspondingly equal to the three sides of this triangle ABC, therefore those two triangles can go into each other according to side rule. Okay, again, we should hold on that triangle MEB can go, this is the side can go to triangle EBC according to side rule. And for the fact that those two triangles can go into each other, we derive that they are also the same areas. That is to say, we derive that the area of this triangle MEB is equal to the area of this triangle EBC. And again, we derive that the area of triangle MEB is equal to the area of triangle EBC. Because they can go into each other. In the next step, we found out the area of this triangle MEB. The area of triangle MEB will be equal to the base of the triangle, that is MB times the height AE over 2. So again, the area of triangle MEB in total is equals to the base MB times the height AE over 2. MB is 1, AE is also 1. MB is 1, AE is also 1, and you have to divide it by 2. 1 times 1 is 1, so in total the area of the big triangle MEB is equal to 1 half square units in size. If the area of triangle MEB is equal to 1 half square units in size. So I can write it that the area of triangle MEB is equal to 1 half square units in size. And from this equation, we derive that the area of triangle EBC is also equal to 1 half square units in size. Okay. Actually, because they can go into each other, they must have also the same area. So if the area of triangle EMB is equal to 1 half, then the area of triangle EBC must be also equal to 1 because they can go into each other. So the area of triangle MEB plus the area of triangle EBC equals to the area of triangle MEB is 1/2 plus the area of triangle ABC is also 1/2, so 1/2 plus 1/2 is 1. So in total, we should find out that the sum of the areas of those two triangles is equal to 1 square units. But quadrilateral EMBC consists of those two triangles. Again, the big quadrilateral EMBC consists of those two triangles and not anything else. And therefore, the area of the big quadrilateral MEBC must be equal to the area of triangle EMBC, that is 1/2, plus the area of this triangle EBC, that is also 1/2. 1/2 plus 1/2 is 1. Repeat again. The area of this big quadrilateral EMBC of the big quadrilateral EMBC must be equal to the sum of the areas of the two triangles that it consists of. That is to say, it must be equal to the area of triangle MEB plus the area of triangle EBC. The area of triangle MEB is 1/2 plus the area of triangle EBC, that is also 1/2. 1/2 plus 1/2 is 1. So in total, we should find out that the area of the big quadrilateral EMBC equals to 1. So we can write it that the area of the big quadrilateral EMBC is equal to 1 square units in size. But quadrilateral EMBC consists of those two shapes. This is the green right triangle EMB, this is quadrilateral ABCE. And therefore, the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of the big quadrilateral EMBC must be equal to the area of the first shape, that is the area of the green right triangle EAM, plus the area of quadrilateral EABC, plus the area of triangle ABC. Again, the area of quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is the area of the right triangle EAM plus the area of quadrilateral ABC. And from this equation, the area of quadrilateral EMBC equals to 1 equals to the area of triangle EAM plus the area of quadrilateral ABCE. We will derive that 1 equals to the area of triangle EAM plus the area of quadrilateral ABCE. And again, we derive that the area of triangle EAM plus the area of quadrilateral ABCE equals to 1. And the area of triangle EAM plus the area of quadrilateral ABCE is equal to 1. Those two sides are equal to each other. So I copy this equation here. So in total, we found out that the area of triangle EAM plus the area of quadrilateral ABC equals to 1. But according to our definition, the area of triangle EMA equals to Z square units in size. So we can substitute the area of triangle EAM plus Z, and we get that Z plus the area of quadrilateral ABC equals to 1. Okay, Z plus the area of quadrilateral ABC equals to 1. Our task is to find out the area of this big pentagon ABCDE. The area of pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. And quadrilateral ABCDE consists of those two shapes. Those two shapes is not anymore. That is to say, therefore, the area of quadrilateral ABCD must be equal to the area of the first shape, that is the area of this right green triangle EDC plus the area of this quadrilateral ABCE. Repeat again, the area of the big pentagon ABCD must be equal to the area of the two shapes that it consists of. That is to say, it must be equal to the area of the green right triangle EDC plus the area of quadrilateral ABCE. We already found out that the area of the green right triangle EDC equals to Z square units in size, so we can substitute the area of triangle EDC by Z. So total, the area of the big pentagon ABCD is equal to Z plus the area of quadrilateral ABCE. Again, the area of the big pentagon ABCD equals to Z plus the area of quadrilateral ABCE. But we already found out that the area that Z plus the area of quadrilateral ABCE equals to 1. So Z plus the area of quadrilateral ABCD equals to 1. I copied this equation here. Z plus the quadrilateral ABCDE equals to Z plus the area of quadrilateral ABCE equals to 1. And from this long equation, we derive that the area of pentagon ABCDE equals to 1 square inch in size. Again, the area of the big pentagon ABCD equals to 1 square inch in size. And that is the answer to the first question. In the next step, I will present you the second question, and I repeat on the solution that we have to on the second question. The second question, our task is to find out the area of this green shape. The green shape is actually triangle A and B, so we have to find out the area of this green triangle A and B. It is given us the question that chord AB is the diameter of this circle. In addition, we know that AP equals to 9 units in its length, AP equals to 9 units in its length, PQ equals to 4 units in its length, PQ is the tangent to the circle at point M. Those two angles are both right angles. Again, our task is to find out the area of this green shape that is actually the green triangle A and B. So first of all, we can implement the rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. This is peripheral angle A and B that subtend on chord AB, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its size, according to rule 7. This is angle PAM, is equals to alpha degrees in its size. And we define this angle PAM as alpha. So in the right angle PAM, this angle, in the right angle PAM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in an triangle. So PQ is a tangent. PQ is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? We have this angle that is 90 degrees minus alpha. This angle is 90 degrees. Plus this angle that is 90 degrees, plus this missing angle BMQ, total must be equal to 180 degrees according to rule 3. Okay, again. The sum of the angles on the upper side of the straight line PQ point M must be equal to 180 degrees. That is to say 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ, total must be equal to 180 degrees according to rule 3. 90 degrees plus 90 degrees, it is 180 degrees. Plus the missing angle BMQ minus alpha equals to 180 degrees. Here we have 180 degrees on both sides of the equation, so 180 degrees will get cancelled, and we left only if the missing angle BMQ minus alpha equals to 0. Here we added alpha to this equation, and we found out that the missing angle BMQ equals to alpha degrees in its size. This is the missing angle BMQ, this equals to alpha degrees in its size. So in this small right angle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in an triangle is equal to 180 degrees. It is very easy to see that the big right angle APM is similar to this small right angle BMQ. I'll explain anyway why those two materials are similar to each other. First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if we found out that all the figures of this big right triangle APM are corresponding equal to all the figures of this small right triangle BMQ, and therefore those two right triangles are similar to each other according to angle similarity rule. Because again, if we found out that the big right triangle APM is similar, this is the sign of similar, to the small right triangle BMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of this small right triangle BMQ. Okay, again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP is 9. Over MQ. MQ is the missing side, so we leave it as it is. PM is the missing side, so leave it as it is. Over BQ. BQ is 4. So if we found out that 9 over MQ equals to PM over 4. Here we cross multiply this equation, and we found out that 9 times 4 is 36 equals to MQ times PM. Again, 36 equals to MQ times PM. In the next step, we define the center of this circle. This point is point O, and we join points O and M together by straight line. Point O is the center of the circle, point M is the point of the circle itself, so OM is the radius of the circle that we define the R. So here OA equals to R, OB also equals to R, because they are both the radius of the circle is equal to R. So here we can implement rule 1 because we have the radius OM that is equals to R. The radius OM is 1 to point M, that is the point of tendency PQ with this circle. And whenever your radius is 1 to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did the construction. The next step we did the construction, that is to say from point O, that is the center of the circle, we go perpendicular on AP. Again, from point O, we go perpendicular on AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP, this point is point A. By doing this construction, quadrilateral NO, MP. Quadrilateral NO, MP, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4 triangle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in a quadrilateral is equal to 360 degrees. And therefore this 4 triangle must be equal to 90 degrees in its size. So in quadrilateral NOMP we have 4 rectangles, and according to rule 5, in the quadrilateral that is 4 rectangles must be this rectangle in front of the square. So we relate to quadrilateral NOMP is a rectangle because it has 4 rectangles. In the next step, we did another construction, that is to say from point B, we draw perpendicular on the radius OM. Again, from point B, we draw perpendicular on the radius OM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. By doing this construction, we create quadrilateral SBQM. In quadrilateral SBQM, we have 1, 2, 3 rectangles, and therefore this 4 angles equal to 90 degrees in its size. And therefore quadrilateral SBQM, that is 4 rectangles, it is a rectangle. So we know that the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP is parallel to the opposite side OM. but LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, then the straight line AP itself must be parallel to the other straight line OM. Therefore, AP is parallel to OM. Yeah, AP is parallel to OM. The next step, I copy those two parallel lines and reduce AOB and the diameter AOB in the new page, and represented all 50 in the new drawing. So this is 978 bit that is parallel to OM. This is the diameter AOB that touches the two parallels at points A and O. So those two angles are defined as corresponding angles and are located between the parallel lines AP and OM, and therefore they must be equal to each other on their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta. According to rule 50, so I repeat quickly on rule 50. According to rule 50, corresponding angles between parallel lines are equal to each other. In the drawing we have line A that is parallel to line B. The red line C cuts those two parallel lines and those 2 points. Those two angles on the alpha and beta are defined as corresponding angles and are located between the parallels A and B. And therefore are equal to each other in their sizes. That is to say alpha equals to beta. We have only implemented rule 50 in our drawing. Repeat again. Those two angles are defined as corresponding angles and are located between the parallels AP and OM, and therefore according to rule 50 they are equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta according to rule 50. So if you found out that angle PAO equals to beta, this angle PAO, this is equal to beta divided in size, and angle MOB also equals to beta. This angle MOB is also equals to beta. So in this triangle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus beta, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, the right triangle A and O, this angle equals to beta, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus beta, according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right triangles can go into each other according to angle side angle rule. According to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to beta, and therefore they are equal to each other. In addition, those two sides AO and OB, they are both the radius of the circle is equal to R, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So we shall prove that the right triangle ALO congruent, this is the sign of congruent to the right triangle OSB according to angle side angle rule. This is to say, we should prove that those two angles and the side that is included between those two angles, that is AO is equal to R, in the right triangle ALO, are correspondingly equal to those two angles, and the side that is included between those two angles, that is OB, is equal to R, in the right triangle OSB. And therefore, those two right triangles can go into each other according to angle side angle rule. We have those two angles and the side that is included between those two angles in the right triangle ALO corresponding equal to those two angles, and the side that is included between those two angles, that is OB, in the right triangle OSB. And therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we derive that side ALO of the right triangle ALO is equal to side SB of the right triangle OSB. Those two sides are equal to each other. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides, that is to say ALO and SB, must be also equal to each other and their lengths. We can form that ALO equals to SB. So if we define ALO as X, then SB must be also equal to X because they are equal to each other. But we have the rule that the opposite sides of a rectangle are equal to each other. So in the big rectangle LOMP, side LO is equal to the opposite side PM. But LO equals to X, therefore PM must be also equal to X. Likewise, in the small rectangle SBQM, side SB must be equal to the opposite side SMQ. Again, side SB must be equal to the opposite side MQ. But SB equals to X, and therefore the opposite side MQ must be also equal to X units in its length. We already found out that MQ times PM equals to 36. MQ is X and PM is also X. Again, MQ is X and PM is X. So in total, X times X equals to 36. X times X is X squared, so X squared equals to 36. Here we took out all those equations and we found out that X equals to the square root of 36, that is 6. So here X equals to 6. Here also X equals to 6. In the next step, we implement the Pythagoras theorem on this right small triangle BMQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle BMQ, BM squared is the square of the hypotenuse equals to BQ squared plus MQ squared. And again, the right small triangle BMQ, BM squared equals to BQ squared plus MQ squared. BM is the missing side, so we notice it is, and this equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16, plus QM squared. QM squared. QM is 6, therefore QM squared is 6 squared, that is 36. So in total, we found out that BM squared equals to 16 plus 36. 16 plus 36 is 52. So in total, we found out that BM squared equals to 52. Here we took out all those equations and we found out that BM equals to the square root of 52 units in its length. This is the missing hypotenuse BM, it is equals to the square root of 52 units in its length. In the next step, we implemented the Pythagoras theorem in this right big triangle APM. According to the Pythagoras theorem, in this right APM, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. Okay, again, the right big triangle APM, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. AM is the missing side, so we have to see this. So it is AM squared equals to AP squared. AP is 9, therefore AP squared is 9 squared, that is 81, plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, we have all that AM squared equals to 81 plus 36. 81 plus 36 is 117. So in total, we found out that AM squared equals to 117. Here we took out all those equations and we found out that the missing hypotenuse AM is equals to the square root of 117 units in its length. This is the hypotenuse AM, that is equals to the square root of 117 square units in its length. Our test is to find out they have this green shape, but the green shape is actually the right green triangle AMB, so we have to find out they have the right green triangle AMB. The area of the right green triangle AMB will be equal to the base MB times the right MA over 2. So again, the area of the right triangle AMB will be equal to the base MB times the height AM over 2. We already found out that MB equals to the square root of 52 units in its length times AM. AM equals to the square root of 117 square units in its length. So in total, MB times AM over 2 equals to the square root of 52 times the square root of 117 over 2. We have the algebraic identity that says that the square root of A times the square root of B equals to the square root of A times B. And therefore, the square root of 52 times the square root of 117 will be equal to the square root of 52 times 117 divided by 2. 52 times 117 is 6084 divided by 2. The square root of 684 is 78 divided by 2. 78 over 2 is 39. So in total we should find out that the area that we are looking for in this question, that is the area of this ring shape A and B, is equal to 39 square inches in size. Okay, again I should find out that the area of the ring shape is equal to 39 square inches in size. Okay, thank you very much.